Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series on applied electronics. In this lecture, we will be having the following contents: Debye temperature, Debye's T cube formula, merits and demerits of Debye model, the density of states histogram, lattice vibrations, one dimensional monatomic lattice. As I told you in the previous lecture, because Einstein considered the solid as made up of atoms, and all atoms are assumed to vibrate with the same frequency, he obviously can get only one frequency, a discrete frequency with which all atoms will be vibrating. On the other hand, assumed of Debye that the solid is a continuum, right? It is not made up of atoms. Anyway, you have come back to the atomic nature of a solid at a later stage, and but initially what he did was to consider the solid as a continuum, and he talked about elastic waves which are traversing through the solid. Waves means will have different wavelengths and frequencies, and so you got a frequency spectrum. Number of modes will be having distinction that you have Debye spectrum and the Einstein spectrum. What we have done so far is to obtain how many modes of vibrations. Suppose this is nu and this is d nu, okay, this is nu and this is nu plus d nu, there is a small frequency range. In this frequency range, in a given frequency range, how many modes are there? You have nu here, nu plus d nu here, and how many modes of vibrations are there in this frequency range? This is the number of modes, right? The possible number of modes you have to have, that is what we have calculated. So, with every mode, what is the energy associated? What we did in Einstein cases, we had 3n oscillators, and the 3n oscillators multiplied by energy associated with each and every oscillator. Similarly, now you have got how many modes are there, with each and every mode what is the energy associated with each and every mode, that has to be multiplied. That is what we have to do to determine the energy. Why do you want to get the energy? Because your specific heat Cv is nothing but dE by dt, where E is the energy, right. If E is the energy, dE by dt derivative of energy with respect to temperature will give you the specific heat, right, Cv. So, I will come back to the difference between Cv and Cp. At this point of time, I should tell you we will be always using the thermodynamics, and we will be using for all theoretical purposes, we will calculate what is called Cv. What is V? V is the volume, specific heat calculated at constant volume, right. Calculate Cv because of the simple fact Cv is equal to dE by dt. Once you get the energy, derivative of this energy with respect to temperature will give you Cv. That is the reason why all theoreticians they aim to obtain an expression for Cv. But on the other hand, what experimentalists measure is Cp, the specific heat at constant pressure, And what is the difference between Cp and Cv? I mean, these things I have not discussed so far. I will come to these things a bit later, but a point I want to tell you at this stage is the difference between Cp and Cv is very small, nearly 3%, but one should remember experimentally what you measure is Cp, theoretically what you get is Cv. All the Debye formula, Einstein's formula, or the classical formula, all these things we will have Cv. So, you should not be getting confused what is Cv and what is Cp. Experimentally what you measure is Cp, the specific heat at constant pressure. Theoretically all of us will be arriving at an expression for Cv. Why do you want to obtain Cv? Because Cv is related to dE by dt. Once you get the energy, the derivative of the energy with respect to temperature will give you Cv. Okay. Cv and Cp can be compared and comparable because the difference is negligible, it is very small. Okay. That is what you do. Now, how will you get Cv? As I told you, dE by dt. So, E is you obtain in all the theoretical approaches. What you try to get is the energy of the solid. Okay. Now, we have got so many modes. So, with each and every mode, what is the energy associated? For every mode, what is the, or with every atom, what is the energy associated with the atom? When it is vibrating, what is the energy associated with every atom? According to Max Planck, the harmonic oscillators have different energy levels. You have to, that is what was done by Einstein. He wrote down your energy is equal to 3n times nh nu. Okay. Now, we go to the Debye model. Let us see what is it we are trying to do. Associated with each and every vibration mode, a harmonic oscillator of the same frequency, the vibration of the crystal becomes this multiplied by h nu by e to the power of h nu by kT minus 1. How do you get this? From the quantum theory again, the mean energy of the oscillator can be shown to be equal to h nu by e to the power of h nu by kT minus 1. Every frequency with which you have a mode of vibration, right, the different modes of vibrations are there. You have got every frequency, the energy associated will be h nu divided by e to the power of h nu by kT minus 1. Okay. So, you multiply the total number of modes, the energy associated with every mode is this much, is the total number of modes multiplied by the energy associated with each mode will give you the total energy of the solid. This is what you have to determine. Okay. Now, you determine this E, that is this is what you have as the expression for the total number of modes will be given by the expression of this kind, that multiplied by nu square into h nu by e to the power h nu by kT minus 1 to d nu. Okay. They are all constants. Then you have got h nu multiplied by nu square becomes h nu cube, this is the same denominator remains the same into d nu. Let us have the variables h nu by kT to be equal to x, make the substitutions, h nu by kT is equal to x and h nu d by kT to be equal to xm. What is h nu d by kT? Nu d is the maximum frequency, that is the reason why you have xm. H nu by kT, any frequency will be x, whereas h nu d is the maximum frequency, that Debye cutoff frequency, that you have it as xm. Now, in the place of nu d you will be having kT by h into xm, is that right? And in the place of h nu by kT, that can be substituted by x. So, therefore, making these substitutions, we will be having your E to be equal to 9n times kT by h nu d by to the power of 3 into this integral varying from 0 to xm. In the place of xm we had nu d, right, that Debye cutoff frequency, the same instead of the Debye cutoff frequency, now we have replaced that by x or xm. So, maximum thing will be xm. So, x cube dx by e to the power of x minus 1, that is the final expression that we are getting for the energy of the solid according to Debye. Following the expression E equal to kT, one defines a Debye temperature by E is equal to kT, right. In the place of kT, in the place of temperature T, you put theta d, that will be equal to E is equal to h nu. Now, for maximum frequency you should have nu d. Theta d corresponds to maximum, theta d refers to what is called a very important Debye temperature. In the place of T, I substitute theta d, that will be equal to h times nu d. Nu d is the Debye cutoff frequency or the maximum frequency. So, how do you define theta d? The theta d, the important parameter which is used in very many other areas to study the different physical properties like electrical resistivity or superconducting behavior, try to explain very many other properties. You come across Debye temperature, the very important Debye temperature theta d becomes obviously equal to h nu d by k. This is a Debye temperature in Kelvin or centigrade. So, h nu d by k T will be equal to theta d by T obviously. Debye temperature is often called as stiffness constant. It is because of the fact that as it is a measure of the lattice stiffness or the melting point. There is a rule called Lindemann rule which says Tm, the melting temperature, depends upon the Debye temperature. The higher the Debye temperature, the melting temperature will be higher, or vice versa. Okay. Whenever solids have high melting temperature, your Debye temperature will be higher. So, stiffness means what? The lattice is stiff. Stiff means it is difficult to break. The melting point is higher means what? The bond cannot be easily broken. So, tungsten when compared to other metals in a periodic table, tungsten will have higher melting point. Melting point is higher means what? The interatomic potential or the bonding is very strong. I told you in the earlier lectures also, if the interatomic bonding is very strong, you say the melting point should be strong, because cutting the bond will be difficult, breaking the bond will be difficult. So, it refers to the stiffness of the lattice. So, lattice stiffness refers to the fact that the higher lattice stiffness refers to higher melting point. A higher melting point will indicate a higher Debye temperature. Okay. The Debye temperature is related to many other physical properties. Okay. And I am now mentioning about the Lindemann rule. Substituting the above expressions in the equation that you have for the total energy, we have there are two cases. Case 1, the temperature well above the Debye value, the Debye temperature theta d. Now, you consider two regimes, one T temperature well above the Debye temperature, and obviously the temperature below the Debye temperature. The theta d will be generally in the range of 300 to 400 Kelvin, and of course, you know, the highest Debye temperature is possessed by beryllium, right, not tungsten. So, it is not only the stiffness alone deciding factor, there are other things which decide the Debye temperature. So, beryllium has got the highest Debye temperature, that you should note, and so you got two regimes, T greater than theta d. For very high temperatures, x is small, your Debye temperature will be coming here in the place of T. For very high Debye temperature, when theta d is very large, obviously x will be small. Okay. That is what I am trying to tell you here. You go to high temperature regime, T greater than much greater than theta d, x is small, and hence we make the approximation. The approximation that you have for the energy, the x square here, okay, to the power of theta d by T comes in the upper limit for the integral that you have got here. E will become equal to 3 r T. Okay. There are simple mathematical steps. You can look at the mathematical Nk. Nk is r, then you got T by theta d to the power of 3, then again you got theta d by T to the power of 3. Finally, that will reduce to 3 nt nkt or 3 r T. And what is Cv? The derivative of this energy with respect to temperature. Obviously, you will end up with 3 r. That is what was shown by Dulong and Petit. Cv will be equal to 3 r, even though that has not been mentioned very much in the earlier lectures, but in the previous lecture I wrote Cv is equal to dou E by dou T. Therefore, once you know the energy, you should remember whether you have the classical theory or Einstein model or Debye model. In all models or in lattice vibrations, which I will be doing later, in all the models we will try to evaluate the energy of the solid, okay, the thermal energy or any given temperature, the energy possessed by the solid. What do you mean by energy possessed by solid? The atoms are vibrating, right. The vibration energy or the total energy possessed by a solid will be evaluated at any given temperature. Then you have to find the derivative of this energy with respect to temperature. So, in the high temperature regime you have your Cv equal to 3 R, as was expected. It is along the lines that one expects, because the experimental observations show that Cv equal to 3 R, okay. That is the Duolong and Petit's law. You go to the other regime, T much lesser than theta d, when temperature goes much below the Debye temperature. That is the important thing, because what we could not explain on the basis of classical theory or Einstein model is that the classical theory absolutely is independent of temperature. It cannot explain the variation of heat capacity with temperature. On the other hand, the Einstein model showed a fall which was much faster than what it should be, that is exponential fall, but experiments indicated the fall should be following a T cube law. Now we have to see whether such a T cube law are obtained using the Debye model. You have the case 2, for very low temperatures T much lesser than theta d, the upper limit is infinity, then this becomes integrand, the integral x cube dx by e to the power of x minus 1 becomes equal to pi to the power of 4 by 15. This upon substitution in the expression for energy, that becomes E becomes 9n kT into kT by h nu d to the power of 3 into pi to the power of 4 by 15. That makes your energy to be equal to 3 by 5, because you have got 9 by 15, that becomes 3 by 5, then pi to the power of 4 is here, n kT is here, then your this becomes T by, because theta, what is theta d? H nu d by k, h nu d by k is theta d, that comes in the denominator, theta d to the power of 3. Thus the energy of the solid becomes proportional to T to the power of 4, you have got T here, T cube here, the energy becomes proportional to the power of 4. That implies what? You have to find the derivative for determining the heat capacity. So, differentiating with respect to temperature, obviously you will be getting your Cv will be, if you have d by dt, this T will go off, the other things will remain, right. d by dt on the temperature, derivative of the energy with respect to temperature. So, everything will remain excepting this T, that is the T by theta d cube will be there. So, Cv finally turns out to be 12 by 5 into pi to the power of 4 n k into T by theta d whole cube. That comes out to be 263 times n k into T by theta d to the power of 3, or 940 into T by theta d whole cube. The important thing to be understood is Cv is proportional to T cube, right. Cv varies as T cube and is a famous Debye's T cube law. You see Cv is here on the left hand side, Cv is directly proportional to T cube. That is what we tried very hard to obtain, because experiments clearly indicate that the variation of Cv with respect to temperature follows a T cube law, and finally Debye could show that he could obtain a T cube law, right, which is in very fine agreement with the experimental observations. Okay. That is a very positive thing, that is your Debye's T cube law, Debye's theory is in the right direction, because it is able to explain the experimental observation. There is an excellent agreement between the theory and experiments performed on a large number of elemental solids as well as compounds, as is seen from this curve. This curve shows the theoretical curve given by Debye, the theoretical curve. The continuous thing is obviously the theoretical curve, right. Following this formula, you have the formula, you will be having only because your T is here. So, T very high temperatures, okay. Then you go down to low temperatures, you substitute, what you do is you vary T from 1000 to namely some 0, right, 1000, 950, 900, then 300, 250, 40, 20 and so on, right. So, this obviously is a theoretical curve, okay, this is a theoretical curve. Now, what about experimental points? Now, for aluminum you have the plus, wherever you have got plus here, that refers to heat capacity measured. For aluminum you have got plus here, right, for aluminum as a function of temperature. They are all at T by theta, Cv measured as a function of T by theta, where theta is the Debye temperature, okay. For calcium fluoride they are indicated by circles. You see the circle here, then you have got circle here, circle here. Now, there is a very fine agreement. Then again copper, you find the triangle, you got triangle here, you see a triangle, triangle and so on, you got triangles. The all triangles or circles or the plus signs indicating the variation of heat capacity. For aluminum, an ionic solid like calcium fluoride, again a metal like copper, all of them falling on the theoretical curve. That shows there is excellent agreement between the experimental points and the theoretical curve. So, the Debye theory is in perfect agreement with the experimental observations. So, measured specifics for various metals and compounds are shown. Also, the important thing is the horizontal line. So, you see the classical theory, it showed that Cv is equal to 3 R, right, 6 calories per mole, right, this it ends at 6, right. All the observations made at room temperature, they showed the value to be 5.96 calories per mole, 6 calories per mole per degree Kelvin, okay. Therefore, in the high temperature limit, the Debye's theory, it agrees with the classical theory. The Debye's theory is in perfect agreement at the high temperature limit. Now, you see here when T equal to 1.2 or so, then it falls to drop down, and this drop cannot be explained on the basis of classical theory for a simple reason. The classical theory does not take into account the temperature at all, right. Cv is equal to simply 3 R. The Einstein model, it showed a curve which was much steeper, the fall was more exponential. This is a thing that I showed earlier, that the Einstein curve went like this, right. It was, the fall was much faster than what the experiments indicate, right. So, that is the reason why the Einstein model has to be rejected. So, you end up with the Debye model. Now, whatever that you get in the Debye model, are you convinced, or further experiments do they all show that the Debye model is perfectly acceptable? It is not so. Let us see the merits of Debye model. Indeed, Debye model is one of the very important models, and the Debye temperature, even till today, it has got immense relevance, because very many physical properties are expressed in terms of the Debye temperature, right, the stiffness constant. Therefore, the Debye model is indeed a very important model. It has been able to successfully reproduce the experimental results. That is the first thing. Assuming Ct equal to Cl, the velocity is transverse than Cl, to be equal to 10 to the power of 3 meters per second as the velocity of sound, and since n by v is of this magnitude, the Debye cutoff frequency will be around 10 to the power of 13 per second, right, the frequency. The maximum frequency of vibration in the solid is 10 to the 13 hertz, and that shows the what you get from the Debye model is an agreement with a realistic solid, and this corresponds to a minimum wavelength of 1 angstrom, a minimum wavelength. So, what is the distance that separates the atoms? The atomic separations are on the order of around 3 to 5 angstroms. All solids that you have got, the the interatomic distance will be from something like 2 to 5 angstroms, right, or 3 to 5 angstroms. Therefore, the minimum wavelength is of the order of 5 angstroms, 1 angstrom. This shows that the wavelengths propagated through the solid are of several angstroms, and this justifies the Debay's assumption of the solid being treated as a continuum. The universal curve connecting CV and T by theta d is called a universal curve because of the fact that it satisfies all kinds of solids, the metals and compounds. So, it is called a universal curve obtained by Debye for a metal or a compound, alloys and so on. The universal curve that you have here connecting CV and T by theta d is found that the experimental points for different solids fall on the universal curve. It is called a universal curve because it satisfies the elemental metals and compounds as well, alloys and so on. Let us go to again, when we propose every theory, there will be certain drawbacks or shortcomings or defects in the theoretical model. Nothing is perfect, right. You cannot define the solid in a perfect way, taking into so that the theories will be exhausted. So, you have to go on, right, still further. So, the demerit of the Debye model is the following. You have experiments by which you can study what are called the lattice vibrations. You have a solid is made up of atoms, the atoms are all vibrating. You can have a spring, you can think of a spring, the solids, the atoms are vibrating. The atomic vibrations are called lattice vibrations, and the lattice vibrations you have the demerit for a simple reason, the density of states which could be obtained experimentally, it goes like this, a continuous line, right. Okay. There is a experimental density of states curve that is definitely in disagreement with the Debye's theoretical model. The demerit of Debye model, as you see in the graph, you have got density of states as a function of frequency. The experimental curve is the solid line. Okay. You have see a dip here, right. You see a dip and then it goes up and so on. But on the other hand, when you look at the Debye curve drawn by broken curve, this shows a continuous increase in the density of states, right. Then you come across the omega d, the angular frequency corresponding to the Debye temperature. It comes here, it does not show any dip or the variation that is experimentally observed is not shown by the Debye model. Debye model is incapable of showing the experimental observations with regard to the density of states. Now, this density of states I will be talking about electrons. Now, I am talking about the elastic waves, or truly speaking I am talking about phonons. The experimental curve is obtained from the neutron diffraction experiments, about which I will talk in detail later. Now, let me go to the summary part of today's lecture. The agreement between the experimental observation and the theoretical curve, that is the Debye curve, was found to be excellent. The Debye temperature is of importance. Why is it important? Because very many properties can be or expressed in terms of Debye temperature. So, it plays a very significant role in determining very many properties. The experimental DOS, density of states histogram, differs from that of the Debye model. That is a very important demerit or a disadvantage of the Debye model. So, let us go to the question session. Question number 1, what is Debye cutoff frequency? What are the merits and demerits of the Debye model? Give the dispersion relation connecting omega and k. What is Debye temperature? With this we come to the end of this lecture. The rest of the things we will see in the lectures to come. Thank you.